right, so when we last left our chemistry heroes, we had just looked at situations where you were given the concentration of either hydronium or hydroxide ions, and you had to say, yes, that's greater than 1.0 times 10 to the negative 7th molar, or that's less than, and you could assign it acidic or basic. Well, that's not usually the way this works. Usually the way this works is you're just given a solution, and a concentration of a solution, and you have to go about calculating your hydronium and hydroxide ion concentrations from there. Okay, so the first thing that you need to know is that we are only going to do this with strong acids and bases, because we can only talk about things that will completely ionize, that will ionize to the fullest extent that they could possibly ionize. So we're not going to talk about any weak acids or bases because we can't calculate those, because we don't have a way of knowing how many molecules have ionized at any given point. Okay? So let's take sodium hydroxide, our old friend. What did we use sodium hydroxide for? What did we use it for in class? Actually, we did use the sodium hydroxide solution on the ornaments. And we also used it in our soap making. That was a big component of our soap making. Okay, so we have an equation here for the what of sodium hydroxide. What is this? This is dissociation, because it's an ionic compound, so it is splitting up into the ions that are already there. And if we have 1 mole of sodium hydroxide, how many moles of hydroxide ions do we get? 1. We get 1 mole of hydroxide ions. This goes back to the dissociation stoichiometry that you did in chapter, 13 or 14, where we can look at a given number of moles of an ionic compound or a molecular compound and figure out how many moles of ions it will generate when it goes into solution. Okay, questions? So if this was 2 moles of sodium hydroxide, we would produce 2 moles of hydroxide ions. If this was a half a mole of sodium hydroxide, we'd produce half a mole of hydroxide ions. And that's true for any number we can name. So that's an important point to think about, actually, because we're not usually dealing with as much as a whole mole of hydroxide ions. Okay, so thinking about that dissociation of sodium hydroxide, and we talked about real simple cases like a one mole of sodium hydroxide, or 1 mole of sodium hydroxide, and how many moles of ions it would generate. What if we have a solution of sodium hydroxide? Can we figure out how many moles there are there? Sure, because a 1 molar solution is just equal to 1 mole in 1 liter, right? That's easy enough. Well, what if we have a 1.0 times 10 to the negative 2nd molar solution of sodium hydroxide? Can we figure out the concentration of hydroxide ions from that? You might suspect that we can, since I'm asking you. Well, to start off, we have to think back to what that molar concentration means. It just means that in every 1 liter of solution we have 1.0 times 10 to the negative 2nd moles of sodium hydroxide. That's not a lot of sodium hydroxide. That's, what, a centimole? It's a small amount. Okay. Well, we know from this dissociation equation that we did that every mole of sodium hydroxide that we dissociate is going to produce 1 to 1. It's going to produce 1 mole of hydroxide ions. So we can multiply this by that conversion factor. We'll get 1 mole of hydroxide ions for every 1 mole of sodium hydroxide that we put in. So what that means is we have 1.0 times 10 to the negative 2nd moles of hydroxide ions in every 1 liter of this solution. Does that make sense? Do we want to run through that again? Okay, so let's do this step by step. we've got a 1.0 times 10 to the negative third molar, whoops, I forgot my big M there, molar solution of potassium hydroxide. We want to know the concentration of hydroxide ions in this solution. Okay. If you're going to break this down into the simplest possible steps, the first thing you want to do is write the dissociation equation for potassium hydroxide. So we have potassium hydroxide in a solid form. And now so the coefficients in front of those ions tell you what the relationship is. That tells you how many moles of hydroxide ions you're going to produce for every mole of the substance that you dissociate. Okay? Simple enough? Good. Next step is we want to know how many moles of hydroxide are going to be formed from this. So we're going to set up a factor label. So the first box we would create would just be really what it means that we have a 1.0 times 10 to the third molar solution. We're just going to write the relationship between the moles and liters. So we know that in 1 liter of solution, we have 1.0 times 10 to the negative third moles. It's like a millimole. Okay, well, now what we want to know is how many moles of hydroxide we're going to generate for every mole of potassium hydroxide that we dissociate. So we know we have to have the same units in chemical down here, moles of potassium hydroxide, and up here we want moles of hydroxide. Well, it is 1 to 1. And now what this is going to end up telling us is how many moles of potassium hydroxide, we're going to have in each liter of solution, because those are the things that cancel out. And so our answer is 1 times 10 to the negative third moles of hydroxide ions, in 1 liter of solution. So 1.0 times 10 to the negative third is equal to the concentration of hydroxide ions in this solution. And that would be our answer to that question. Okay, if we're given a solution of barium hydroxide, 1.0 times 10 to the negative fourth molar barium hydroxide. These keep getting more dilute, don't they? It's crazy. We want to know the hydroxide ion concentration. Okay, so what if we have something a little bit more complicated, like we've got barium hydroxide? So, this is not a straight 1-to-1, is it? First thing we want to do is write that dissociation equation. What's going to be different here? How many hydroxide ions will every mole of barium hydroxide create? 2. We're going to generate 2 moles of hydroxide ions for every 1 mole of barium hydroxide now. So this is going to change our math a little bit. Okay, so now we want to write a factor label that expresses what this really means. So 1.0 times 10 to the negative fourth moles of barium hydroxide in every 1 liter of solution. Okay. And then the next box in our factor label is going to use this mole ratio from our dissociation equation. So we know that for every 1 mole of barium hydroxide that we dissociate, we're going to get 2 moles of hydroxide ions. Okay, so for every 1 mole, or for every 1 liter of this particular solution of barium hydroxide, we are going to have 2.0 times 10 to the negative fourth moles of hydroxide ions. Fairly simple. We will start tomorrow with doing these kind of problems with ionization. So with things like HCl, hydrogen chloride, and hydrogen bromide, and sulfuric acid, things like that. So questions, comments? We'll pick this up tomorrow.